All right. This video, almost nothing new. We have a new name, but it's actually just the old name in disguise. So here's what we're looking at now. What if we use the right color? What if now we're looking at the region between two curves being rotated about an axis? I'm not even going to try to draw this picture, but the answer is going to be the washer method. Let's look at the book's picture. So if we're looking at this region between two different curves rotated about the x-axis, then if you look at a tiny region, this is a shape that you're getting. Instead of a disc, it looks like a washer or a donut or something. A flat donut. You didn't let the yeast give it time to rise or something. I don't know. And so, again, you don't have to remember washer or disc method at all. You can just think of adding up cross-sectional areas like we did at the start, the first couple videos of this section, right? And it's just integrating the area of this washer. Well, what is that area of that washer? Again, let's look at this little region. Maybe there's that little region down here. And we're looking at this washer. What does this area look like? Well, let's draw it. What is the area of this red shape? Well, if this top function is f and this bottom function is g, that means, again, this is f and the bottom one's g. This area is just the full area minus the blank area. Well, the full area is pi times f squared, and the blank area is just pi times g squared. So that's the washer method. The end. Cut the video. I could. You already know how to do these problems. But we could formalize it. But basically, I don't want to write it all out again. The washer method. Cliff Notes version. Similar to disc method. But R is a region under F and over G. So again, we are going to require that F, that's not going to fit. We are going to require that F of X is at least G of X on this interval. Then the volume is just going to be pi, because again, you can factor out a pi from both of these. The integral from a to b of f of x squared minus g of x squared dx. Again, this is if rotated about the x-axis. Or you get a very, very similar formula if you're rotating about the y-axis. My head's going to be in the way. Okay. And again, if you look at these volumes, you can just think about it as, well, what's the volume of that outer shape? What's the volume of the inner shape? And then just, well, how do you, there we go. I'll be invisible, transparent, translucent. You just subtract those volumes to get that middle volume. Again, another way of seeing this is go over here. This volume is just the volume of the outer one minus this blank inner volume. And there you go. If you want to write it all out, there's the washer method. It's in the book. Let's do some examples. Example 6. Find the volume of a solid of revolution formed by rotating the region bounded above by f and below on by g on the interval from 1 to 4. Part A is going to be f of x equals x, g of x equals 1 over x, and about the x-axis. So let's get a picture. So you have the function. I need to color code these. Let's look at the function f of x equals x. Oh, already got the color coding wrong. F of x equals x. G of x equals 1 over x. From 1 to 4. They intersect at 1 comma 1. If you plug in x equals 1, you'll get that that's where they intersect. The 4. So we're really looking at this region right here. We're rotating that region about the x-axis. So again, I could try to draw this picture. It's going to be a little hard. You know what? I'm going to try it. So we have a straight line here. We got like a curved line here. And we're rotating this about the x-axis. Kind of like this. And it's this volume right here. It's a hollow volume. All right, look at this beautiful picture. It's terrible. But the idea is we'll use the washer method. Okay, I'm not keeping this picture up. Try to draw it. I hope you do a better job than I do. So this is our region here. All right, now this volume, whoa, wrong color, is just going to be pi times the integral. X is going from 1 to 4 of f squared minus g squared dx. Chapter 2 is over. Just chapter 1, just evaluating this integral now. F squared is x squared. G squared is 1 over x squared. I highly recommend you pause the video, complete this integral on your own, and see if we get the same answer. And we're going to get 1/3 x cubed plus 1 over x. We get that plus 1 over x from the power rule. Write this as x to the negative second. Evaluated from 1 to 4, or just pi times, this becomes 64/3 plus 1/4 minus 1/3 plus 1. And we'll have to simplify this a little bit. Okay, so that's going to be pi times, we need a common denominator. This becomes 192 twelfths plus 3 twelfths minus 4/3. 4/3 is 16 twelfths. There's got to be, I should use a calculator for this. We get 195 minus 16 is 179 twelfths. Units cubed. You can bet I'm checking my answer on this one. All right, so we're looking at the integral. Pi times the integral from, is it 1 to 4 again? I don't even remember. Yeah, it was. Of just x squared minus 1 over x squared dx. And is that 179 pi over 12? No, it's not. Okay, so x squared minus 1 over x squared. Yeah, we just, let's be smart about it. Let's let the antiderivative be 1/3 x cubed plus 1 over x. We have f of 4. We have f of 1. And if we have pi times f of 4 minus f of 1, we indeed have the right answer. So f of 4 is 259/12. Oh, I multiplied this by 3 instead of 4. That's what the problem was. So multiply by 4, we get 256/12, which is why the 259/12 comes in. And then we're going to get our final answer of f of 4 minus f of 1. Simplifies down to 81/4. Always good to check your answers. There it is. That's our volume. So now, part B. This time I do want to make the uglier region for part B. In the last one, I didn't want to, and so I had to rewrite the problem. But now I want you to use the same R, but now rotated about the y-axis. And this should be tricky. I haven't done this. I created this problem. Usually I take these from the book. This should be tricky. But I'm curious what we get. So what I'm going to do is I'm going to copy this to a new page. So we can use the exact same figure. Oops. But now we're rotating it around a different axis. So this is where things get hard. Because again, this is the equation y equals x. And this is the equation y equals 1 over x. But if we're rotating it like this, it's upper and lower. You're rotating it around the x-axis. It's outer and inner. You're rotating it around the other axis. But now the outer function is this. And the inner function, well, sometimes it's that. And sometimes the inner function is this. Let's blow this up a little bit. Right? Here's what we have as our region. This is the point 1, 1. It goes up here, down here, and this is our region of integration. We have to split this up into 2 pieces because we're rotating it like this. All right. This first piece is this area, which again is mirrored. Like so. This region that's getting rotated around. Can't really draw a picture. It's very hard. And then we're going to have to add the volume from the other one as well. So there's going to be 2 of them. V1 and V2. And V2 is going to look like that region rotated around the y-axis. So let's do them one at a time. V1 is going to be pi times the integral. Now we're in y coordinates. We're rotating around the y-axis. We need y coordinates. And it's not upper minus lower. It's outer minus inner. That would be a good thing to add to the DIS method in your notes, honestly. Or the washer method in your notes. Right here is upper. And that's lower. Not lover, lower. So we pretend that's a W. And then down here That's outer minus inner. Okay, because it's right and left instead of up and down. Right and left instead of top and bottom. That's another way of saying it. Top, bottom, right, left. Okay, so... Oh, we don't need this. I think I copied it twice. Oh, also, we're a little out of order. These should be switched. All right. Okay, so now in this V1, the y coordinate starts at y equals 1, and it goes up to whatever this y coordinate is. Well, let's look at the picture. It's y equals x, and x equals 4, so that's going to be a y coordinate of 4. Now, what's the rightmost function? Using the washer method, this rightmost function, because again, thinking sideways in terms of y, that's the line x equals 4. Okay, so it's just going to be 4 squared. Now it's the leftmost. That's going to be this guy. What's that line? That's the line x equals what? Again, this guy right here is x equals 4. This guy right here is x equals y. Right? If y equals x, then x equals y is the same curve. So this becomes y squared dy. And this is what we integrate for V1. And we do something very similar for V2. What's the rightmost? Well, the rightmost is still 4. What's the leftmost? Well, rightmost again is still x equals 4. The leftmost is y equals 1 over x, which is the same as x equals 1 over y. So we get 1 over y squared like this. What are the limits for this one? This one's maybe a little trickier. The upper y limit is still y equals 1. The lower y limit, let's look at this graph instead. When x equals 4, what is y? 1/4. It goes from 1/4 up to 1 here. And you can do both of those integrals on your own. I'll go through them quickly, but again, I highly recommend you pause the video and work them out. We're going to get pi times, this becomes, skipping steps, 16y minus 1/3 y cubed from 1 to 4. 4 times 16 is 64 minus 16/3 minus, and you plug in 1 is 16 minus 1/3. Skipping steps has never gotten me in trouble before. And you could simplify that out. And I will use a calculator this time, just to save some time. 64 minus 16/3 minus 16 minus 1/3 is 43. Huh. Okay, 43 pi. That seems huge. So I'm going to check my answer. Pi times the integral from 1 to 4 of 16 minus y squared dy. That is not the answer I had, 43 pi. Is 16y minus 1/3 y cubed. 64/3 is y. 64/3 is right there. This makes a lot more sense now. 27. Oops, why am I adding zeros? 27 pi is exactly what we wanted. Good. And on the bottom, you can do the same thing. Antiderivative is going to be 16 plus now 1 over y, evaluated from 1/4 up to 1. 16y rather. And when you do that, you're going to get 16 plus 1 minus 1/4 of 16 is 4 plus 4. All right, surely I can do this one in my head. That's 17 minus 8 is 9. This bottom integral should be 9 pi. And indeed, if we check, integral from 1/4 up to 1 of 16 minus 1 over y squared dy is indeed 9 pi. I don't need to check that. That's 9 pi. So our volume is just adding these together, 36 pi. That's our answer. Units cubed. And that's how you can find more complicated volumes of surfaces of revolution. Again, it's for revolving around the y-axis, it's always right minus left. So if you have these complex regions, the right and the left might change, and then you're gonna have to split it up into multiple ones. I don't think that happens very frequently, but it's something to be aware of, and it's something that could happen. Let me know if you have any questions, and that's the end of the section.